And so today we are moving into the realm of hypothesis testing, okay? Okay, and so we discussed hypothesis testing very briefly prior to the midterm exam, but we're going to delve a lot more deeper into it today, and we're going to today is November 5th. Man, it's already November. They're playing Christmas music, and I went to Costco. Well, actually, Costco was stocking the wrapping paper last month already, but well, anyway, okay, November. Here we are. Okay, hypothesis testing. Okay, so the idea behind hypothesis testing is just like all of other statistical inference. We have a population that we wish to know about. Oh, yes. I will dim the lights. Okay, and from this population, we have a random sample. Okay, and based on what we see in the sample, we want to make a conclusion about the population. Okay, and so we often, with hypothesis testing, the way we, well, so let me just contrast hypothesis testing with confidence intervals. They're kind of like two sides to the same coin. With confidence intervals, we look at the sample and just kind of let the data speak for itself and say, based on what we see in the sample, we think the mean of the population is between here and here. That's with a confidence interval. With hypothesis testing, we start off with kind of a claim, and we say, someone says, I think the hypothesis, I mean not the hypothesis, I think the population has this property. And then we say, okay, well, if that's the case, could I end up with this data that I have? So with hypothesis testing, we start off with a hypothesis and we use our data to test that hypothesis. With confidence intervals, we don't start off with a hypothesis. We just take data and say, what can I infer from this data? All right, so where did my cursor go? So with confidence intervals, data. Okay, with hypothesis testing, Okay, and so with hypothesis testing, we always have a pair of hypotheses, okay? The first hypothesis is known as the null hypothesis, and the second one is the alternative hypothesis. Okay, so symbolically we write the null hypothesis as H naught or H0. This is kind of the quote status quo, or this is, we are testing this hypothesis. Okay. Generally, if we want to make some kind of interesting finding, we're almost hoping that at the end of our study we're going to reject the null hypothesis. Okay, so if we wish to make an quote interesting finding, we hope to reject the null hypothesis, because this rejecting the null hypothesis means we have data to make a conclusion. If we don't reject the null hypothesis, it just means our study was inconclusive. Okay. So key idea is the null hypothesis will always have an equal sign in it. Maybe I'll write that out, equal sign. Okay, and by having an equal sign in it, it makes the hypothesis testable. We can test against this claim or something that the parameter in our population is equal to something. If it's just kind of this vague thing saying the population parameter is not equal to some number, our data cannot really be used to make any kind of conclusive decision. Okay, so when we set up our alternative hypothesis, okay, the HA, symbolically, I don't know if I'm spelling this correctly, probably not. It looks identical to the null hypothesis, except the equal sign has been replaced with either a not equal sign or a greater than or a less than. If we use a not equal sign, then we have what is known as a two-tail or a non-directional test. And if we have either a greater than or a less than sign, this is known as a one-tail or one-sided or a directional test. This is kind of getting into the mechanics of hypothesis testing. Okay. All right. And so conceptually, okay. All right. So conceptually, when we carry out our test, perform a hypothesis test, we calculate a p-value. Okay. And so what a p-value is, this is the p-value is equal, or I'll say the p-value is the probability of observing the data we have or something more extreme if the null hypothesis is assumed to be true. Okay, so this is a definition that you should memorize. I think I wrote this in your notes, or you should have this in your notes from prior to the midterm, but it's a very important concept, so we'll have it written out here again. And the idea goes something like this, okay? So let's say our null hypothesis says something like the mean of the population is equal to 120, okay? So here are our null hypothesis says the mean of our population is 120. Okay? So if the null hypothesis is true, if we assume the null hypothesis is true, okay, whenever we take random samples from this population, our random samples should have a sample mean close to 120, right? And we know this because of the central limit theorem, right? When we take random samples from the population, have a mean y bar close to 120. So far, does that make sense? Our line of thinking? Okay. So let's say our random sample has a mean of 103. Okay. And so we want to say, well, random sampling will produce sample means that are not exactly the same as the population mean. But how often will we get a sample mean of 103? That's what we want to know. Okay? And when we say something more extreme, we say, well, 103 is 17 units away from 120. So what's the probability we get something basically 17 units or even farther away from what we expect? So we're expecting random samples to produce means close to 120. We got something that's 17 units away from 120. So what's the probability we get 103 or something more negative? Or on the other side, it would be what? 137 or more positive. Okay. And do we know how to answer this question? Okay. Well, based on the central limit theorem, if we have the mean of the population, we can do it. Okay. Not the mean. If we have the standard deviation of the population, we can do it, right? So we say, let's say our random sample has a mean of 103. So our p-value is basically, what is the probability that a random sample taken from a population of 120 with a mean of 120 ends up having a sample mean of 103 or less, or 137 or more. I'll write this out. Okay. P-value is equal to probability that a random sample Okay. All right, and so the answer to this question, when we calculate our p-value, we can do apply the central limit theorem and do these kind of probability calculations. Okay, I think we learned that in chapter 5, doing these calculations for random samples. Once we do that, we're going to get this probability, okay? So let's say the probability, we'll have two different scenarios here, okay? Well, I guess before I move on, I just want to make sure, is the definition of the p-value and how the p-value is applied in our problem here okay with everyone? Okay, so let's say we do the math. Okay, so I haven't given you any kind of other information that we would need, but let's say we do the math, and our p-value ends up equal to 0.21. What does this mean? We go through the process, okay, and our p-value ends up being 0.21. What does it mean to have a p-value of 0.21?
This is a 21% chance that it's 103 or lower, 137 or greater.
Yeah, it's open. Yeah, so what this says is that just random sampling, just from the process of random sampling, a random sample could end up having a sample mean of 103 or less, or 137 or more, about 21% of the time, just from random chance. Okay? So this says, so what this means is that there is about a 1 in 5 chance that a random sample could end up with a sample mean with a y bar of 103 or something more extreme. I'm just going to write something more extreme rather than writing out 103 or less or 137 or more. Okay? So would you say this provides evidence against the notion that the mean of the population is 120, or does this not provide evidence against the notion? So let's write this. Okay. So our question is, does our data provide evidence against the claim that the population has a mean of 120? What would you say? So what are we thinking? So our sample has a mean of 103. Someone claims that the population has a mean of 120. So we say, well, let's assume the population has a mean of 120. What's the probability that random samples from a population with mean 120 produces a random sample with a mean of 103? We do that math. That math turns out the answer is 0.21. So does that feel like that there's a high probability of getting a sample of 103 or a low probability? What are we thinking here? Okay, so I would say if this were the case, my conclusion is our data does not provide evidence evidence against the claim that mu equals 120. Why? Because my probability being 0.21 is too big for me to just dismiss, okay? My p-value of 0.21 is too large for me to dismiss. There is certainly it is certainly possible that my sample of 103 is just a result of random chance, okay? There is a non-negligible probability that my data could have resulted from random chance alone. So I'll let this sink in for a little bit. The random chance comes from the random sampling aspect, okay? So what I'm saying is that after doing the math, I find out that a random sample could arrive with a mean of 103 20% of the time. Okay? So I'm not ready to conclude that that this provides evidence against the mean of 120. Okay? So here, I guess, here's a situation, right? If you laid out 5 pieces, 5 cards, okay, and one of them is an ace, and you tell a friend, you know, just grab a card, see if you can get the ace, and the card, and the friend reaches out, grabs a card, and he picks out the ace. Would you then, would you just say he got lucky or he cheated? You would probably say he just got lucky, right? If there's 1 in 5 and he grabbed the ace, I mean, there's a possibility he might have cheated, but 1 in 5 is also, it's not that out of the question for someone to just get it by luck. Okay. On the other hand, if you laid out 1,000 cards and only one of them was an ace, and you say just pick a card at random, and he grabs the ace, do you feel like he cheated, or do you think he also just got lucky that time? Yeah, with 1 in 1,000, you're less likely to believe he just got lucky. Okay, you're thinking, yeah, you probably peeked or you knew something. I mean, he could have been lucky, but the probability that he was just lucky is 1 in 1,000. Okay. On the other hand, when there's only 5 cards and he gets it right, you'd say, well, you could have just been one of the lucky 1 in 5. Does that reasoning make sense? And so here, when you get a p-value of 0.21, basically we're saying the data we have could have just been a result of coincidence or random chance, because it happens, something like this happens from random chance about 20% of the time, over 20% of the time. Okay? Yes?
So how low does the p-value have to be before
Yeah.
it raises your eyebrows?
Exactly. That's a great question. I'm gonna just write the exact same scenario, this time with a smaller p-value, and then we'll get into a discussion of what is a big and small p-value. Okay? And that, I'm glad that you raised that question, because that is the question I'm trying to evoke in you guys. So, okay. So this is so I'm just going to continue on from this scenario. So now this is scenario 2. We have the exact same setup, 120, have a sample mean of 103. This time we do the math, and then our p-value ends up being, we'll say 0.0001. Okay? So this is same scenario, except we do the math, and the p-value ends up equaling 0.001. Okay? And so this time, this means this time our p-value indicates that we could get the data we have, or something more extreme. From random chance or random sampling. But the probability of that happening is only 1 in 1,000. Okay? And so my conclusion here, so if somebody says, does our data provide evidence against the claim that mu equals 120? This time, my answer, my conclusion is yes. Is yes. Our data provides evidence against the claim that mu equals 120. Basically, my p-value is small, enough where I can comfortably dismiss the possibility that my data was actually just a random coincidence. Okay. So, it could have happened by random coincidence. So I want us to acknowledge that when our p-value is 0.001, the data we have, what this says is that our data could have resulted from random coincidence. But there's only about a 1 in 1,000 chance that our data happens by random coincidence. And so because it's so small, we can kind of dismiss this notion and say, it probably didn't happen by random coincidence. And rather, our initial assumption that mu is 120, that's probably the thing that's wrong. Okay? So we say, we dismiss the possibility that my data resulted from random coincidence. The fact that I do have this data then indicates to me that my initial assumption that mu is 120 is probably wrong, or is wrong. Okay? So I'll write this down. The fact that I do have data with y bar equal to 120 tells me that my initial assumption is wrong. Okay? And so this is the process of hypothesis testing. We start off with some kind of premise. We take our data and we say, hey, I have this data. Could the data I have resulted from random chance under the assumption of the null hypothesis? If the probability of getting the data that we have is high, we say, well, maybe the null hypothesis is true after all, and I got this from random chance alone. If, on the other hand, our probability is really small, we say, the fact that I have this data and the fact that the probability of me getting this data from random chance alone is incredibly tiny makes me believe that my initial assumption is wrong. Okay, and so that's what we have here. I just want to make sure this kind of line of thinking makes sense to everybody, because this is how all of hypothesis testing is going to go with this line of reasoning. And so if this is confusing to you, let me know, because we should get it sorted out here rather than, I don't know, 3 tests later, or 3, I should say, types of hypothesis tests later. Okay. Okay, so there's a very good question of what is considered to be a high p-value and what is considered to be a low p-value. How do we decide when we should reject the null, come to the conclusion of rejecting the null hypothesis or not rejecting the null hypothesis? Okay, so this is the question, okay, and this is important because our rules for making conclusions is basically along the lines of this. If the p-value is big, do not reject the null hypothesis. We do not have evidence against the claim made in the null hypothesis, our data could be a random chance. Okay, and then the other conclusion is if the p-value is small, okay, reject the null hypothesis. We have evidence. Against the claim made in the null hypothesis, our data is unlikely to have been a result. Random chance alone, okay? So when do we decide our p-value is high or big? When do we decide if our p-value is small? Okay. Well, it's kind of arbitrary. So basically the rule is we choose an arbitrary value known as alpha, and this is our significance level. Okay, and so basically if the p-value is greater than our arbitrarily chosen alpha, it's big, and if our p-value is less than our arbitrarily chosen alpha, it's small. Okay, and so just over the course of time, you know, studies have been done to see what is the correct choice of alpha, and there's no definitive conclusion, but kind of over the course of time, the accepted value for alpha is 0.05, okay? So just, I guess by tradition, we often use alpha equal to 0.05, basically 5%. This has become the value of alpha that we use most often. It's kind of, for better or worse, become the value necessary to kind of get papers published in lots of journals. You need a p-value less than 0.05. There's nothing magical about this number. It is an arbitrarily chosen number. The true value should probably be something around 0.05, but there's nothing magical about the value 0.05 in of itself. Okay, so the true choice of alpha, you know, probably should be around 0.5. there is nothing, quote, magical about 0.05. It is arbitrary. But that's okay, and that doesn't mean it's bad. For example, we have arbitrary values that we have just come to accept in life, and so for example, the age you are considered an adult in the United States is age 18. There's nothing magical about that number. It probably should be something around 18 because studies have shown that a person's brain continues to develop until around that age, 17, 18, 19, 20, something around there. And so by the time you're 18 or around 18, you are able to make conscious decisions that could affect your future. But there's nothing that really distinguishes somebody who's 17 and 364 days old and someone who's 18. But for legal purposes, when you turn 18, you can join the military and buy drugs that are whatever, you know, and not illegal drugs, but you can buy cigarettes and vote and, you know, do all of these things. But there's nothing there. So studies have been done. The p-value probably should be something around 0.05, but I guess just because we have 5 fingers on our hand, you know, 0.05 is convenient, and that's what we use. But depending on the circumstance, you might very well choose, you as the researcher get to choose your choice of alpha. You can choose a small alpha if you want. You can choose alpha to be 0.01, or you could choose alpha to be 0.10, 0.10, depending on the circumstance. And we can have a discussion about that, okay? So, as a researcher, okay, you have power, or I guess you have the ability to choose alpha, okay? And so, you know, other common choices of alpha are, you know, 0.01 to 0.10. Anything in between generally is considered acceptable. But your choice of alpha will affect the possibility of making an error. And these are errors inherent to the process of hypothesis testing. So I have to discuss errors. Here, let me just write this. Okay. So your choice of alpha has a direct consequence on making errors in hypothesis testing, okay? And these are not like mathematical or calculation errors. These are just errors inherent to the process one R, 2 R's? Huh? 1, 2, 1. Okay. 1 R. Inherent to the process of hypothesis testing, or essentially, basically, making a conclusion with incomplete, you know, with limited data. If you don't have all the information, there's just an inherent possibility of making a mistake. All right, and so the conclusions you make are either to reject the null hypothesis, conclude that you have evidence against some claim, or your conclusion could be not to reject the null hypothesis. You conclude that you don't have evidence against the null hypothesis, okay? So keep that in mind. So our conclusions could be, so I'm going to make a little table here. Could be that we do not have evidence, do not have enough evidence to reject the null hypothesis, or we conclude we do have enough evidence to reject the null hypothesis. Okay, so these are our two possible conclusions, and the reality could be that the null hypothesis is true, or the reality could be is that the null hypothesis is not true. And so if the null hypothesis is true, and our conclusion is that we don't have enough evidence to reject the null hypothesis, this is actually what we want to do. This is the correct decision. And if the reality is that the null hypothesis is not true, the correct decision is to reject the null. So this is also the correct decision. Okay? And so ideally, whenever the null hypothesis is true, we conclude that we don't have evidence against the null hypothesis. That's ideally what we do. And ideally, whenever the null hypothesis is wrong, we come to the conclusion that we do have evidence against the null hypothesis. Okay, does that sound good? Okay. However, because we're in a situation where we don't have all the information, sometimes we don't make the right decision. And this is just inherent to any decision-making process. Sometimes the null hypothesis is true, but from random sampling you get a weird-looking sample, and it misguides you or misleads you into believing that the null hypothesis is wrong. So this is incorrectly rejecting the null hypothesis. Okay, and this error is known as a type 1 error. This is just, we did not get very creative in naming these errors. Oftentimes, sometimes this is called a false positive. But the terminology is not standardized on this, okay? And then the other thing would be that we incorrectly failed to reject the null hypothesis. So over here, the null hypothesis is not true, but for whatever reason, our data did not lead us to this conclusion. So maybe we didn't gather enough data, so we our conclusion was inconclusive, or maybe our data happened to be a fluke that made us to believe that the null hypothesis is not wrong. Okay, so maybe in reality the mean is 100. The hypothesis is that it's 120, but from random sampling, maybe our sample mean ended up like 119, and we're like, well, we're not going to reject the null. Okay, but that's wrong, right? And so this is known as a type 2 error. Or sometimes called a false negative. Okay. All right, so let's think about how would our choice of alpha affect either type 1 or type 2 error. If I use a really small alpha, if I use alpha equal to 0.01, am I more likely or less likely to commit a type 1 error? So think about this. With alpha equal to 0.01, when do we reject the null hypothesis? We would reject the null hypothesis when our p-value is what in comparison to our alpha?
Less.
Okay, so we reject the null hypothesis when our p-value is less than alpha. So if I'm choosing alpha to now be 0.01 rather than the regular old 0.05, am I more likely or less likely to reject the null hypothesis? I'm less likely to reject the null hypothesis, okay? So I am less likely to reject the null hypothesis. So does that mean will I be making the mistake of incorrectly rejecting the null hypothesis more or less often? So I'm just rejecting the null hypothesis less often in general now. So I'll be making this error less often, okay? The type 1 error, incorrectly rejecting the null hypothesis, can only happen if you rejected the null hypothesis, right? That can only happen if you reject the null hypothesis. And if you're rejecting the null hypothesis less often now, you're just going to be less likely to make this mistake, okay? If you do less of something, you're less likely to do that thing wrong, okay? So choosing a small alpha leads to fewer rejections of the null hypothesis. And that just, in general, rejecting the null hypothesis less often means fewer cases of incorrectly rejecting our null hypothesis. And it turns out, whoops, what is this? Okay, sorry. Turns out that the probability of a type 1 error is equal to alpha itself. So if alpha is 1%, we're going to make a type 1 error 1% of the time, because our p-value ends up being less than 1% of the time. Okay, so alpha is directly linked to the probability of a type 1 error. And on the other hand, choosing a large alpha leads to rejecting the null hypothesis more and increases our risk of type 1 error. Okay, so large alpha increases probability of type 1 error. Okay. And on the flip side, if you are rejecting the null less often, you are now increasing the risk of type 2 error. Just because inherently type 2 error, if you're rejecting less often, that means you're not rejecting more often, because you're either rejecting or not rejecting. So if you're not rejecting more often, now you're increasing the chance of not rejecting incorrectly, right? And it's like a tongue twister and brain twister here, but you know, if you're doing something more often or less often, the probability of a mistake happening with that thing goes up or goes down depending on whether you're doing it more or less frequently. So type 2 error, the probability of type 2 error is just assigned a character beta. Okay, and I'm going to flip to the next slide. So probability of a type 2 error is just assigned this character beta. Beta is the second letter of the Greek alphabet, or equivalent to B. That's the probability of type 2 error. We don't have any choice of beta. This is kind of inherent to, or this beta is a result of several factors. So we don't have a choice over beta. Okay, but in general, okay, if we use the same data, okay, so assuming we're using the same data, we're not changing anything else, okay, alpha goes up means beta goes down. And then if alpha goes down, it means beta goes up. Okay. We give a special term to the quantity 1 minus beta. Okay, so whenever we do 1 minus a probability, what is that? That's the probability of the complement, right? So what would the complement of a type 2 error be? This term is known as power. So a type 2 error is incorrectly failing to reject the null hypothesis. So the complement of that would be okay, well here, let's, so type 2 error is failing to reject the null when the null is false. So the complement of failing to reject the null when the null is false is rejecting the null when the null is false. Okay, so 1 minus beta, we give it the name power, and this is the probability of correctly rejecting the null when the null is false. So that's the this square. This square, this is the power square. Okay. Power of this decision, or probability of that decision is power. Rejecting the null when the null is false. Okay? So alpha goes up means beta goes down, but power goes up. And when beta goes up, power goes down. Okay, so high power is a good thing. That's our ability to make a decision. Sometimes it's known as the sensitivity of a test. Okay, so I'm going to kind of describe a couple scenarios where in one situation we want a large alpha, and in another situation we want a small alpha. Okay, so imagine a criminal trial. Okay, so in a criminal trial, what is our null hypothesis and what is our alternative hypothesis? Okay, so one of them is that the defendant is guilty, and the other one is going to be that the defendant is innocent. So which is the one that we assume to be true, and we use our evidence against that? So which one do we assume to be true? We assume innocence, right? We always say, you know, well, they don't have cops on TV that show cops, but you guys all remember it. But like the young class, they're like, "What are you talking about?" But at the end of these shows, they always say, those arrested are always presumed innocent until proven guilty in a court of law, right? So in our null hypothesis, we assume the defendant is innocent, innocent. And then the alternative is the defendant is guilty. And it's up to the prosecution to provide evidence that says, hey, we've got enough evidence here so that there's no way this evidence could have been produced if this guy is innocent, and therefore the jury would conclude guilty. That's the prosecution's job, right? And the defense, all they have to do is say, oh, this evidence is no good, right? This evidence could have happened from, this evidence is circumstantial, it could have just been a result of this and that, right? You could have hit that cell tower, could have pinged the cell tower and not actually have been at the scene of the murder for whatever reason, okay? Did you guys ever listen to Serial Podcast? Okay, so this is like the right demographic to to ask that question. So the question is, defendant innocent or defendant guilty, okay? Evidence is provided by the prosecution to convince the jury that the null hypothesis is not true. Okay? So in our ideal world, if the defendant is guilty, what happens? In the ideal world, whenever the defendant is guilty, the jury convicts. Okay, so in that case, jury rejects the null hypothesis. Okay, and then ideal world, whenever the defendant is innocent, the jury would what? Acquit. Is that spelled right? Basically, do not reject, or does not reject the null hypothesis. Okay. But in any situation where you don't have all the information available, you are bound to make mistakes. So what is a type 1 error and what is a type 2 error? So in this setup, what is a type 1 error? Type 1 error is incorrectly rejecting the null when the null is true. Type 2 error is failing to reject the null when the null is false. So in this scenario, what's a type 1? Yeah, so type 1 would be rejecting the null, or a jury convicts but the defendant is innocent. Okay. And what would a type 2 error be?
They don't convict.
Yeah, the jury acquits but the defendant is actually guilty. Okay. Now, ideally, we don't make either kind of mistake, but we also know that's not possible, right? There's errors. Errors are just going to happen anytime you're dealing in a situation with incomplete information. So what would you say is the worst type of error? Which error would we rather make if we were forced to make an error? Yeah, we would wait, what did I say? I asked two different questions, right? Yeah, okay. So if we were forced to make an error, we would rather make a type 2 because we consider the type 1 error worse than the type 2 error, okay? At least, you know, and not everyone agrees, but that this is the way our justice system was set up. You know, we prefer type 2 over type 1, okay? Okay, or, you know, type 1 error is worse than type 2. So in this scenario, do we want to use a large alpha or small alpha? We want a small alpha. We want a small alpha to minimize the chance of type 1 error. And they say this in court, right? They don't say use a small alpha, but what do they tell the jury? Beyond a reasonable doubt. They use that phrase, beyond a reasonable doubt, so that the jury doesn't come to the conclusion of guilty based on a hunch. You don't say guilty if the jury just has a feeling that the defendant is guilty. They have to be sure beyond a reasonable doubt, okay, or confident beyond a reasonable doubt to come to a guilty verdict. So I think certain movies like 12 Angry Men are compelling for this reason. The Serial podcast was compelling also because of this reason, because it got into the question of, did they did the jury commit a type 1 error, which you know, gets us thinking, okay? And you know, I think there are, you know, a lot of times we see high-profile cases on TV, and you know, being the armchair detectives, we feel like, oh, for sure this person is guilty, and then the jury comes to a not guilty verdict, and you're like, oh, justice has not been served, or whatever. But that's just how our legal system is set up. It's set up because I think we've recognized that type 1 error would be the worst error here. So in this situation, we want a small alpha. Okay, so let me list off another scenario where we would prefer a large alpha, and then we'll dismiss you guys for a break. Okay. Okay, so let's imagine a scenario. Okay, so let's say like Std testing. Okay. So our null hypothesis and our alternative hypothesis. Null hypothesis would be patient has no disease, and the alternative, patient has the disease. Okay, so they take blood or urine sample or whatever. They're looking for certain things. Okay, so ideally, ideal scenario, anyone with the disease is flagged as having the disease. Okay, and then anyone without disease is cleared. Okay, what would a type 1 error be? And what would a type 2 error be?
Type 1 would be saying they have a disease, but they
Actually do not, right?
Or,
So,
yes.
yeah, type 1 error would be a false positive, basically, okay? And this would be the test says disease, but in reality, patient has no disease. Okay, and what's a type 2 error? Yeah, the test says no disease, but in reality, patient has the disease. Okay, so what would we say is the worst error to make? The false negative, right? I mean, ideally we don't make either kind of mistake, but the false negative would be worse, because now you have somebody who thinks he or she has no disease and could possibly transmit it to other people. Okay, so type 2 error is considered worse. Okay, so in this scenario, we use a large alpha. Okay, and so a lot of these screening tests are made to be very sensitive, and then if you hit positive on any of these tests, they might not say right away, you have the disease. They might say, come in for additional testing, okay, just so we can be sure. But a lot of times these initial screening tests are made very sensitive. Same thing with cancer testing and all sorts of other stuff, because I think the medical community recognizes that it's worse to give someone good news when the reality is grim than to give someone bad news and then later say, oh, the bad news was a mistake, you're actually fine. Okay, we'll take a break here, and we'll come back and we'll do all the actual nitty-gritty of doing